has to do with, like, say if you're comparing chloride and bromide and iodide.
Oh, wouldn't that be more related to what?
It's both. We're going to talk about that. Okay. What they all really come down to, and this is the language that AP is all over right now, is the stability of the conjugate base. What does that mean? Well, when a hydrogen comes off, what does it leave behind? Sorry? It leaves behind the conjugate base. What does it leave behind on the conjugate base? So if I had, like, let's just say I had HCl, and I draw the Lewis structure for that. Yeah? When the H comes off, what does it leave behind? Yes? It leaves behind a lone pair of electrons. Yeah. Okay. So it leaves behind a lone pair of electrons. And the more that the conjugate base is able to accommodate those electrons, the more stable the conjugate base. So if the electrons are like, ooh, comfy place to be, then the acid is going to be stronger because the electrons have a nice comfy home to go to. Now, if they don't have a comfy home to go to, if it's like less accommodating of those extra electrons, then the electrons are like, oh, I might as well just stay attached to this hydrogen here. Yeah? So the more stable the conjugate base is, the more the species will stay in base form, because when we say stable, we also mean low potential energy, yes? And everything wants to go to low potential energy. So the more stable the conjugate base, the stronger the acid. Because it wants to stay in the base form. Okay, so let's talk first about binary acids, which are just H and a single element. So those would be like your HF, HCl, HI. Factor number one, the size of the ion has to do with the stability of the conjugate base. Here we have the electrons left behind by hydrogen, the lone pair of electrons left behind when H plus leaves. And the smaller the anion, the less space there is to accommodate that lone pair. And what do electrons do to other electrons? Electrons repel each other. So if you have, so there's going to be less space, so there's going to be more electron-electron repulsion.
How does H touch?
Okay, you see that bond?
Oh.
That's 2 electrons. Those electrons
Let's stay with Cl.
stay with the Cl. Whoa, that was not good. So we're always looking at that lone pair of electrons left behind by the hydrogen and saying, how happy are they in their environment? Well, if we have a small ion, we have more electron-electron repulsion, so that's going to be less stable. If you have a larger anion, there is more space to accommodate that lone electron pair. And so you're going to have less electron repulsion. And this works when you're comparing any 2 things that are in the same column of the periodic table. Yes?
In a larger anion, I need more electrons.
There are more electrons to begin with, but like they're just more spread out. So an extra pair is kind of like, you can go here, you can go there. Yeah. All right, so if we are in the same column of the periodic table, for example, we might have H2O and H2S, whose conjugate base will be more stable, H2O or H2S? Tell your partner. Whose conjugate base will be more stable, H2O or H2S?
Oh, that's larger than. Oh. Oh, you also have H black.
Oh my gosh. That's long. Okay, I was gonna ask if like. You never showed up. Well, I couldn't wake up this morning. Why?
Who is more stable?
S.
More stable. The larger anion is more able to accommodate the lone pair of electrons left behind when hydrogen dissociates. And therefore, this is a lower potential energy state.
Make this smaller. Less space.
Yep. So there's more electron-electron repulsion. So who would be the stronger acid? H2O or H2S? H2S is the stronger acid. And that's because its conjugate base is more stable. If you were to graph that, for example, if you did a potential energy graph for those electrons, I don't know. I don't like that diagram. I've never seen it before. I just thought it might be helpful. I don't think it is, so let's get rid of it. Okay, excellent. Okay, so the size of the anion has to do with the stability of the conjugate base. So here we, as ion size increases, it's because you have more shells. I shouldn't have just said shells. What's that word they're always looking for? More occupied shells. And I don't think this says anything much different than what we talked about on the previous page. It just kind of gives you the trend as you go down. So if you had H2TE, it would be stronger than H2SE, which would be stronger than H2S, which would be stronger than H2O. You can also argue in terms of bond strength when it comes to, instead of arguing in terms of conjugate base stability, you can argue in terms of bond strength. So in terms of the following hydrogen halides, which is the strongest acid? You could argue this in terms of the stability of the conjugate base based on the size of the anion, but what would happen here?
Like the.
Now, how close are the bonding electrons bond strength? How close are the bonding electrons to the nucleus of our halides? It's going to have the smallest bond length, yes? Yes.
It's like a
A halide is, yeah, a halogen ion. So chloride, fluoride, bromide, iodide, yeah. Good question. And if the bond length is the shortest, what do you know about the attractive forces? Strongest. Therefore, Coulombic attraction is the greatest. Now let's see if I explained that correctly. I think the explanation is probably going to be on the next page. Let's see if we did it correctly. First, consider the bond enthalpy of each of the hydrogen halides. Bond strength can be measured in bond enthalpy. Okay. Atomic radius increases down to group Y. Remind me. More occupied shells. Okay. And,
When H5 was the strongest. Right?
well, we'll get to that. We'll get there. We'll get there. Okay. So here we go. So you can see that it's getting bigger and bigger and bigger and bigger. And as we get, oh, look, so much better drawings than mine. Yes. You can see that the bond length is getting bigger and bigger and bigger and bigger. And as bond length increases, Coulombic attraction decreases because Coulombic force is proportional to 1 over r squared. Yes? Where r is the distance between the charges. Yes? So the shorter the bond, the stronger. The longer the bond, the weaker the bond. I'm going to put bond here because we don't want to confuse that with acid. Okay? If the bond is weaker, what does that tell you about the acid? The acid is stronger because it lets go of its hydrogen more easily. Yes?
Like this does electrolyte why so many electrolytes are about conjugates.
I think so. Yeah. Because electronegativity is a factor as well. But if you were to just look at electronegativity, it always used to bother me because that's all I knew, right? Like I hadn't really thought through these other factors, the bond length, the stability of the conjugate base. I was like, why on earth is HF not the strongest acid? Because fluorine is the most electronegative. You would think it would pull those electrons completely away from hydrogen, but it's not. It's actually, out of the 4, it's the only one that is actually a weak acid. And that's because it has that short bond length, which makes the bond stronger, and its conjugate base is less stable. So between the two of those, that actually makes HF the weakest of the halide acids. Yeah? So HI has the smallest bond enthalpy because it has the longest bond. And therefore HI is the strongest acid. And we could add in here, recall, the largest I minus ion is also best able to accommodate
It's what, that's,
is also best able to accommodate what? Yeah, the lone pair of electrons left behind when hydrogen leaves. Therefore, I minus is the most stable conjugate base. And therefore, HI is the strongest acid. Which of those can accommodate more electrons more easily? The larger one, yes? Now, if you are asked about this, you can pick one. You can pick one of those. I know that AP loves its stable conjugate bases right now. Like that language is popping up hither and yon everywhere. So I might go with that one. But I don't think it matters. I think you could do both. Okay? Whichever one appeals to you more. Okay. So yeah, this just explains, it just summarizes. This is a summary of bond strength due to size of the anion. As we move down a column, the size of the ion increases. The larger the anion, the greater the HX distance. The greater the distance, the weaker the Coulombic attraction. Therefore, the hydrogen is held more loosely and will dissociate more easily, and therefore the acid is stronger. And if we actually look at our bond strength, here is our bond enthalpies. Which bond strength is the strongest? HF. Which bond strength is the weakest? HI. There we go. And this is quoted from an organic chemistry source. I don't know why I have this. Let's find out. HF and HCl and HBr are all binary acids, meaning hydrogen are bonded to the nonmetal. The bond strength of the HX bond, yeah. This is just saying the same thing again and again. So bond strength, so here is the bond strength of the HX bond decreases down a period as atomic radius increases. Therefore, the Coulombic forces become weaker. But also, the larger atomic radii have more area to disperse the lone pair of electrons in the conjugate base than atoms with smaller atomic radii. And what this source said is, while the first reason, the bond strength, is acceptable for first semester organic chemistry students to use to predict, explain, or justify the trend in acid strength, understanding how atomic radius of the acidic element is related to the stability of the conjugate base is more sophisticated. So they're just saying that this is the better reason. Right? They're saying that the stability of the conjugate base is sort of a more sophisticated, lower, like a more base level of explanation. Does that matter to you? No, because you're like a first-year student, right? I don't know. Here is the fundamental concept in organic chemistry. Electrostatic charges, whether they are positive or negative, are more stable when they are spread out than when they are confined to one atom or one smaller space. You can feel free to read through this. I'm not going to. We already talked about it. I don't want to belabor it. Now, we've looked going down a group. What if we go across? No, up is just opposite of down, and for the same reasons, okay? Same reasons up and down. But as we go from left to right, so now we're going across a period.
No, I remember.
It becomes the stability, the electronegativity becomes the defining factor because the stability of the conjugate base becomes more so. The more electronegative element can more easily accommodate the lone electron pair compared with the less electronegative element to the left of it. Yes. Didn't I say they all come back to that? Didn't I say there's 4 factors, but they all come back to the stability of the conjugate base? Okay? They all come back to that. The connection between electronegativity and acidity can be explained that the atom with the higher electronegativity is better able to accommodate the negative charge of the conjugate base. Therefore, it stabilizes the conjugate base. So as we go across a period, what is the trend in electronegativity? Electronegativity increases as we go from left to right across the periodic table. Why?
Like, there's more protons. What's that?
More protons in the nucleus.
More charge. Effective nuclear charge.
There's more protons in the nucleus, but at the same time, there are no more valence shell, occupied shells, but the same number of occupied shells.
Radius decrease. Oh.
So the effective nuclear charge So we have more protons, but the same number of occupied shells. So the number of core electrons is staying the same.
Yeah, so it's minus.
Z minus S, yeah?
Oh, wait, this was. I'm not, like, C minus S is the number.
Z minus S is the number of valence electrons. Except for that the charge would instead be positive. Yes? Because you're looking at how many protons do I have in comparison to the inner electrons. Yes? So as you go from left to right, so the effective nuclear charge increases. And if the effective nuclear charge increases, the Coulombic attraction increases. Coulombic attraction on the electrons increases, therefore electronegativity increases. See why we have to do this stuff in grade 11 before we can do grade 12?
There you go.
Right?
Does regular grade
They do a little bit of electronegativity. I usually don't get around to it in my class because I'm a slow teacher. Yeah.
You're slow teacher.
Yes. I'm probably the slowest chemistry teacher in the school.
What?
Yep. I go faster with you guys because you can take it.
I was like, no way, you're a slow teacher. I was like,
No, I go much faster with you guys because you can hack it. And I'm more willing to assign homework for you to do things like to keep up with concepts because I know that you will do it. Whereas in a regular class, it would be like 1/3 of the people would do it. And then everyone else would just be completely lost. And they wouldn't pick up on it when I went through it. Because I know sometimes you guys don't do it. But sometimes you know, if you haven't done it, you can kind of pick up on the summary I give you the next day, right? You're like, oh, yeah, I got it. And maybe I'll watch it later, right? Yeah.
They just don't get it.
They just don't get it. No. And they don't put in the effort to get it. I think that's the key difference, right?
try to understand.
And I'm not saying that's all of them because obviously there's people in here who were in my regular chem block last year, but how many people in our chem block were like you guys?
It was.
Yeah, they slept through it because it was so slow. Wasn't it slow?
Yeah.
Yeah, it was slow. Slow, like molasses. Yeah. Okay. All right. So electronegativity, what is the trend? Electronegativity increases as we move from left to right. That should be a highlight. As we move from left to right, the number of protons increases, but the number of occupied shells remains constant. So the number of shielding electrons, which is the core electrons,
Miss Spence,
yes,
I have a question.
yes,
I remember last year it was like when we're going down,
yes,
like the 4 electron or
yes, because you have more occupied shells. So yeah, every shell added is a new set of is included in the core electrons, right?
Go that way.
Yeah.
Wouldn't electrons get added?
Electrons do get added, but they all get added to the same shell.
Yeah, right. So then if it goes this way,
yes,
then it would become smaller and smaller.
Yes, because it gets pulled in closer and closer. So the atomic radius gets smaller and smaller.
Right.
Yeah.
But as it's going that way as well, the protons still get added. Right?
Yes.
Oh.
Yes. So you've got more protons, so that brings it in closer and closer, but you don't end up with any more core electrons repelling those outer ones more, so the size just gets smaller and smaller. Yeah. Yeah.
Right. Yeah.
Okay, so the effective nuclear charge, which can be approximated as Z minus S, will increase across a period. Coulombic attraction is proportional to charge.
You have to go stats where you have to go through the you say you have 4 stats, so it has 4.
You're probably okay with that, yeah, because I feel like they don't want huge, long explanations, right? Because the questions have so many parts, and very often things are only worth 1 or 2 marks.
Yeah.
So they don't want you to be like blah 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 blah, which is my weakness. I tend to blah 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 a lot because I want to be clear. Because I'm like, I don't want to lose marks for not having said something that they want to know. Yes. Which I think might help contribute to me being a okay teacher, right? Because, I do sort of tell you everything. On the other hand, I might just confuse matters sometimes. I don't know. Anyway, since Zeth is increasing, Coulombic attraction increases, and therefore electronegativity increases across a row. So I think you might be able to get away with that last sentence there, you know? And therefore, as we go across a row, the strength of the acid increases. When it comes to electronegativity, you can also argue in terms of bond polarity.
What's
Bond polarity. What is bond polarity?
Oh, it's not like which one brand?
Yeah, so if you have a large difference in electronegativity, the bond will be more polar. If you have a small difference in electronegativity between the two atoms, the bond will be less polar. And if you have exactly the same electronegativity, the bond is nonpolar. Yes? No, because hydrogen's always going to be one of the partners, right? So, for example, carbon and hydrogen actually have a fairly similar electronegativity. And so this is not an acid, right? It's just not an acid. No. Lowest electronegativity is going to be francium. Because it's big, it's ginormous, yes. And compared to other things that have the same number of shells, it has the fewest protons. So compared with radium, it's got a smaller of the non-metal. Maybe not. I don't think so. I think it's kind of in the middle, but let's find out. Let's go look. Yeah. Okay, so here we go. We've got phosphorus is 2.1. Yeah, it's on the low end. Boron is 2.0, but boron's kind of almost a metalloid. Yes. So yeah, it's on the very low end of the nonmetals. Yeah? Okay. So if we have a bigger electronegativity in element X, the ability of the atom, what is the definition actually of electronegativity before I give it away?
Like the attraction.
It has to be about bonding electrons. Not any old electrons, but bonding electrons. So electronegativity has to do with bonding electrons. People will often confuse electronegativity with ionization energy, right? Because the properties are related to the same features of the atom, right? The bigger the atom, the less tightly the valence electrons are held, the easier it is to rip it off. But the electronegativity would be, if this is in a bond, what's going to happen to that electron? Not how much energy does it take to get it off. Okay, so it is the ability of an atom to pull bonding electrons towards itself. So if we have a more electronegative atom, we end up with a large bond polarity, and you'll notice that the electron density, there's a lot of density over here, and not very much density on the other side. Yes?
This electronegativity and
They are, I mean, it's not that one causes the other, but they vary because of the same factors. They vary in the same way because of the same factors. Okay? So, electronegativity says, how good am I at pulling electrons away from another atom? Okay, within the bond.
ionization.
Ionization energy says, how much energy does it take to rip off one of my electrons?
It's like how long
Yeah. Now, if we have a less electronegative atom, you're going to have a more even distribution, and the electron density will be closer to the hydrogen. So the hydrogen is held more tightly, and it is easier for the acid to dissociate. Mostly, I see these questions come up in multiple choice around these. So kind of you just need to like be able to recognize which acid's going to be the strongest and have a vague idea of why. I don't know what the likelihood is of having a written response where you're going to have to explain it. But if you do, what's the word you want to use? Stability of the conjugate base. Yes? Those are the words you want to use. Okay. Whew. All right, so here we go. Here is our difference in electronegativity as we go from left to right across period number period number 2. Look at that carbon-hydrogen bond in CH4. Like there's not, like difference in electronegativity is 0.4. So that is a non-polar covalent bond. Okay, we go from that to 0.9. How easy is it for NH3 to give off an electron and become NH2 minus plus H plus? Almost impossible, yes? And when we get to water, how good is water at doing that? It's not as good. It is the weakest of our acids, yes? It's got a Ka value of 1 times 10 to the negative 14. Okay, and HF has a Ka value of 3.5 times 10 to the minus 4. So the increasing bond polarity leads to increasing acidity. Polar bond? Not a polar bond. Okay, we're going to take a breath. Oh, you know what we're going to do? We're going to do a little shoulder thing. Okay, we're all going to stand up. This is really good for your shoulders. Okay? And what we're going to do is we're going to put our...
We actually kind of need this.
Yeah, no, this is actually very good for your shoulders.
No, I think she's.
And what we're going to do is we are going to take our fingers and we're going to curl them like this. Okay?
Yes.
So our palm is flat and we're sticking our thumb out. And then we're going to raise our hands to the side. And then we're going to do 30 circles forward.
Ryan, I'm so blind to you.
Pinch your shoulders together, your shoulder blades together in the back. Okay, try not to fling your body around. You're just using your rotator cuffs to do this, your shoulder muscles. 2, 23, 4. 26, 27, 28, 29, 30. And now what we're going to do is we're going to flip our hands over and we're going to go backwards.
I don't. Imagine, I was just wanted.
20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And now what we're going to do is we're going to put our hands at our temples and we're going to, now we're working on the gliding motion of our shoulder blades. Touch your elbows and we're going to do 15 of these. 2, 3, 4,
Oh, my soul.
5, 6,
Wait, what is this supposed to do?
7,
Yeah, why am I doing this?
8, 9, 10,
Oh.
11, 12, 13, 14, 15. You should do these every day. And now what we're going to do is we're just going to do some shoulder rolls. Okay. Backwards, forward. Shake them out. Do a little just relaxy, swingy thing. Okay. And now we're going to sit back down and we're going to learn about oxy acids. Woo! Many common acids, such as sulfuric acid, contain one or more OH bonds. This is important to remember. In oxy acids, the hydrogens are attached to the oxygen. So we don't attach it to the sulfur. I mean, in this case, it would be hard to attach it to the sulfur, but like with carbonate, people are sometimes tempted to put a fourth bond on the carbon and have the oxygens there, but no, that's not how it works. At first, it may seem confusing that the OH group that we know behaves as a base is also present in some acids. Let's take a closer look at what factors determine whether an OH group behaves as an acid or a base. Well, first of all, when it behaves as a base, what is hydroxide attached to when it behaves as a base? What kind of element?
Oh, the
Alkali metals, alkaline earth metals, right? Here, this is attached by what type of bond? Covalent bond. The bases are attached by an ionic bond to a metal, okay? Right? Is good? So depending on whether OHs are attached covalently or ionically is going to depend on boys. Okay. Alrighty. So here we have some element Y, and then we have our OH. So if Y is a metal, If Y is a metal, then it has a low electronegativity, yes?
Yeah.
And that means the bonding electrons are going to move from the low negativity to the high negativity. So what you end up with then is you end up with a metal plus, and those electrons there are like, I don't want to stay with the metal, I would rather hang out with the nonmetal, and that's how you get a base. Yes? But if Y is a non-metal, the bond is covalent, M plus, yeah. If Y is a non-metal, the O is bonded, is covalent, and the substance does not readily use its electrons. So generally, as the electronegativity of Y increases, and if you remember, electronegativity increases as we go that direction on the periodic table, yes? Up and to the right? Yeah. As the electronegativity of the element to which Y, the oxygen, is attached to, so does the acidity of the substance. So,
This is so tough.
okay, as the electronegativity of this atom here increases, the electron density is shifted towards Y.
Why?
Okay, that's Y, that's O, that's H. So, if that's the case, the electrons that are here are going to be shifted more towards the O and whatever Y is. Yes? So Y could be Cl. Y could be S. Y could be, no, we're not talking about hydroxide groups, we're now talking about like hydroxyl groups, okay? Y could be carbon. Y could be phosphorus. Could be Br. Could be I. Okay, it's going to be a non-metal. And the more electronegative, the easier it is for that hydrogen to fall off. Look at that, we related it back to the stability of the conjugate base. Are we excited? More electronegative elements are better able to accommodate electrons than less electronegative. What? Because it can be a metal. Up here it's a metal. Up here Y is a non-metal. Now Y is a non-metal. What?
How does a non-metal bound?
Covalently,
Like what?
like with a pair of shared electrons.
What's the example of
Like that one.
Oh.
Yes, that is a covalent bond. Yes, yes? Okay. Okay. Generally, as the electronegativity of Y increases, so does the acidity of the substance. Oh, The second reason is because the conjugate base of any acid, YOH, is usually an anion. Its stability generally increases as the electronegativity of Y increases. An electronegative ion produces an inductive effect. Oh my God. I don't want to talk about this. Do you guys want to listen to it?
Yeah.
No?
Is it important?
I don't know how important it is. I don't think it's that important. Feel free to read about it if you want to.
Moving on.
Moving on. Excellent. Okay. So if you had an example of H2CO3 versus HClO3, who would be the stronger acid? Yeah, this is just an example. Yes, but what are we looking at here? We would be saying that since Cl is more electronegative than carbon, its conjugate base will be more stable. You could also say Cl is bigger than carbon, so its conjugate base is more stable. Yes?
Wait, what kind of arrow?
Okay, we are going to talk about the inductive effect, but we're not going to call it the inductive effect. Basically, it just means that if you have two acids, here is CH3, so we got our H's here, H, H, H. If we replace those H's with F's, 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 could you predict which of these two acids is the stronger?
H.
F is more electronegative. So what is it good at? Pulling electrons. Pull, 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 which means that there's an overall directionality that way. Well, because these are pulling on electrons, there's an overall force this way. Yes, that's induction. Okay?
So induction is just like the movement?
The inductive effect that delocalizes the charge of an ion will have a stabilizing effect on that ion. So it is easier for, if this is our negative charge here, it is easier for this negative charge to kind of spread out over those electronegative elements than it is for those electrons to spread out over a non. I wish they would stop screaming. I'm going to close the door. Screaming is distressing me.
Can you just scream out loud?
Well, they're in some classroom somewhere. I have to find them.
Oh, okay, but what's that?
So I do not think you would ever need to explain the inductive effect. I think what you might have to do is you might have to say, I can recognize that this structure, which is identical but has fluorines instead of hydrogens, will make it a stronger acid. Yes? So the more electronegative stuff you've got in your conjugate base, wherever it may be, the more stable the conjugate base will be. Yeah, this is very good. Okay. You can go and look at things if you want to. Now, here we go. Here we're going to compare with the number of oxygen atoms. One of our most famous examples of those is where we have HClO. We have HClO2. We have HClO3. And we have HClO4. Look at those Ka values. Small, bigger, strong acid, strong acid. Why is that? We have more oxygens, so we have more electronegative species on the conjugate base. More oxygens, therefore, there are more electronegative species in the conjugate base. And therefore, the conjugate base is more stable. Yes?
Why is HClO?
Why is HClO what? Oh, because our data table is just some common acids, right? It's not all acids. Yeah, HClO3 is another strong acid. I don't know why it's not on our data table. I don't know. Because we had to limit it. It had to fit on a page. You know what I mean? We didn't want the print to be too small. Carboxylic acids. Those are our CH3COOH. If you had to guess which of these two conjugate bases would be more able to accommodate the extra electrons, which one would you pick just instinctively? The benzoic acid, yes? So any carboxylic acid has resonance structures. It's got 2 resonance structures, yes? So far, so good? Okay.
Oh. No.
I would say benzoic acid. Yeah. Yeah. Okay. That's all. There we go. There's a bunch of questions. They all came from BLB. I don't know how great they are. Mostly I would just, rather than focusing on explanations, I would just be like, which one is stronger? You know, those kind of questions. So you could just get a feel for it. Yes? And then if you want to go into explanations, you can go into explanations. All the answer key, though, it was written before there was this focus on the stability of the conjugate base. So, and I haven't rewritten the answer key because that sounded exhausting. So anyway, there we are. Is it going to come up a lot? I don't think so. All right. So are we good? Okay. We still have 12 minutes left. And because I'm the slow teacher, we are going to go to 6.1b, how to find oxidation numbers. So we are on our yellow book on page 5. Okay, how do we find oxidation numbers? We're on page 5. Oxidation numbers are kind of like a charge. I don't understand why there's still people who don't have their books open to page 5. That is puzzling me. Okay, so they're kind of like the charge. So if we say, what is the charge of Na? Its charge is 0. Its oxidation number, On stands for oxidation number, is 0. If the charge of sodium is plus, then the oxidation number is plus 1. If the oxidation, what is the oxidation number of O in Na2O? 2 minus. Yes? Minus 2. I don't know that it matters whether you write the negative first or afterwards. Now, there are atoms that are bonded covalently and do not actually have charges, and yet we can still find their oxidation number, and we still write them as positive or negative. And don't worry, I'll show you how to do this, and it's actually very straightforward, okay? So, for example, the oxidation number of carbon in the oxalate ion is plus 3. Ooh, imagine that. The oxidation number of carbon in C3H8 is negative 8/3. Wow, that's bizarre, yes? But there is an easy method of finding them. See ya. The oxidation number, here's all the rules. All you got to do is learn the rules, follow the rules, and you're good to go. Any pure element, so any lone element, has an oxidation number of 0. Alkali metals, so these are in compounds. Obviously, if it's a lone element, it would be 0. But if we are in a compound, an alkali ion will always have an oxidation number of plus 1. Does that seem familiar to you? That's its charge. Alkaline earth metals will have an oxidation number of plus 2 because that is its charge. Okay? And these ones are always. Okay? Hydrogen has an oxidation number. What's the most common charge of hydrogen? Plus 1. There's one exception, and that is when you start putting metals with hydrogen, because metals are less electronegative than hydrogen. They will actually give their electrons to hydrogen. It'll become minus 1. Okay? Oxygen has an oxidation number of minus 2. There is also one exception to that. Actually, there's 2 exceptions, but only one common one. And halogens are almost always negative 1. Fluorine is always negative 1. Fluorine can't be anything else, but chlorine, bromine, and iodine have many weird exceptions. That's when you have compounds like ICl5, right? Like those weird compounds that we looked at when we were doing Lewis structures, right? Those are going to have weird oxidation numbers for the halogens. Now, hydrogen's one exception is a hydride ion. It has an oxidation of negative 1. So if you have hydrogen with a metal, and there is a peroxide ion. Most people get all excited about peroxide ions, and every time they see an O2, they think, oh, it's peroxide. It's usually not. Okay, peroxide is usually paired with a metal because it is an ion. Yes? So don't be looking for peroxide in an organic compound. Don't be looking for it. Okay? Do not look for peroxide unless it is hydrogen peroxide or a metal peroxide. Okay? Okay, you're going to have a metal O2. And it has a negative 1. So mostly, you're not going to be looking for 7 and 8. So hydride occurs only when hydrogen is paired with a metal. So you might have sodium hydride, calcium hydride, aluminum hydride. Now you remember, sodium is always plus 1, yes? In order for this compound to be neutral, what does hydrogen have to be? Negative 1. Okay? So that's the reason why it's negative 1 there. Okay? Calcium is 2 plus, so therefore each of your hydrogens have to be, well, you have hydrogen plus, or sorry, hydrogen minus and hydrogen minus. Yes? Minus 1, hydrogen minus 1. Yeah? Okay. You are going to recognize a peroxide because it will look odd. It will look strange. Na2O2? Doesn't that look wrong to you? Yes. CaO2? Does that look wrong?
Yes.
Yes. H2O2, does that look wrong? Yes. That's because they aren't made of regular oxygen ions. They are made of peroxide ions. Okay? So, you got Na plus and Na plus. That gives you 2 positives. So what do the charge of the 2 oxygens have to be?
Negative.
Negative and negative. Calcium is 2 plus. So what is the charge of each oxide ion? Negative and negative. Hydrogen, it's not with a metal, so it's not a hydride. So what is the charge of hydrogen? Plus. And we have 2 of them, H plus, H plus.
So
O minus, O minus. Yes? So don't look for hydrides and peroxides unless they're staring you in the face. Okay? Peroxide is an ion. It will never occur in covalent compounds. Okay? So, how do we go about finding the oxidation number of an element? What we do is we write out the number of each element. So in NH4Cl, we have 1 N, we have 4 hydrogens, and we have 1 chlorine. We are being asked to find what is the oxidation number of nitrogen. That means that we need to already know the oxidation number of hydrogen and chlorine. Do we know the oxidation number of hydrogen? Hydrogen is plus 1. Do we know the oxidation number of chlorine? Yes, it is minus 1. And basically we write out each of our elements and then we make it equal to the overall charge. Well, the overall charge of this compound is 0, right? Because it doesn't have an overall charge, it's a compound.
Right.
And so now what we do is we substitute the plus 1 for hydrogen. We substitute the minus 1 for chloride. And we end up with our little mathematical equation. We have 1 nitrogen plus 4 minus 1 equals 0. So we have nitrogen plus 4 minus 1 equals 0. Nitrogen plus 3 equals 0. So 1 nitrogen is negative 3. So what is the oxidation number of nitrogen? Negative 3. Yeah? We have time for one more. CO2, CO3 2 minus. We have 1 carbon. We have 3 oxygen, and that gives us an overall charge of negative 2. And we're being asked to find what is the oxidation number of carbon in particular. That means we need to know the oxidation number of oxygen. What is the oxidation number of oxygen? It's -2. So we replace the oxygen with a -2. That multiplies out to give you -6. And so one carbon is going to equal -2 plus +6 is +4. So the oxidation number of carbon is +4. Do we like this? Good. Okay.
So whichever one has like an underline.
Whichever one has the underline is the one that you're looking for. And then there's a crazy one here. Okay, we've got our hydrogen, which is +1. We've got our oxygen, which is -2, and this is overall equal to 0. Look at that. Is that not nuts? We end up with +2/3 because we've got 3 carbon and we have to do a division. And so our oxidation number is +2/3. Have a good weekend. Study for your test. I'm going to put one more thing up on Teams. Okay, there's another video for you to watch on electrochem. Okay? Of course there is. I know.
Of course there.
Of course there is. So study for test. And you're going to do 6.1C as also. And if you've not yet done 6.1A, you'll do that as well.
I like binders so fast. Getting faster.
After Monday, you can get rid of
The
chapter 4 or unit 5. Unit 5. Acid base part 2.
That's unit 5?
Yeah.
But that was unit 4.
I get confused.
4 or 5, same thing.
Yeah, who knows?
But, wow, they must like light.
Can you blame them?